We learned the introduction session of the elimination reactions of alkyl halides, that alkyl halides can undergo elimination reactions if they are treated with a base. And in the elimination reaction, the base removes a proton from an adjacent carbon, and there is formation of a carbon-carbon double bond, and there is also departure of the leaving group. So there are three events in any elimination reaction. There is proton abstraction, formation of a carbon-carbon double bond, and departure of the leaving group. So these three events, they can take place at the same time or at different times. If the three events take place at the same time, then it's a second order kinetics elimination, and therefore the mechanism type would be E2. So E for elimination, this is analogous to SN2. So E2 analogous to SN2. So SN2 is a second order nucleophilic substitution. E2 is a second order elimination reaction or bimolecular elimination reaction. Okay, that's also another way to view to interpret E2. So E2 is second order elimination or bimolecular elimination, which means that both reactants, the base and the alkyl halide or the substrate that has a leaving group, they are both important, and the rate of the reaction depends on both, or the rate of the reaction depends on the concentration of both. So again, the elimination reaction is of E2 type if the three steps, the proton abstraction, formation of the carbon-carbon double bond, and departure of the leaving group take place at the same time. Let's show that. So let's begin with E2 then. This is the abbreviation E2, capital E for elimination, 2 for bimolecular. So you can describe this as bimolecular elimination, or second order kinetics elimination. So this is the substrate. With X now, put L instead as a general term or representation of a group that has an ability to leave. And we have here a base. Okay. And we have here a hydrogen. Remember the hydrogen again, as in the introductory session. The hydrogen must be present on an adjacent carbon for the elimination reaction to take place. So the base is going to abstract a proton from a nearby carbon, from an adjacent carbon. So this step is, or this event actually, let's call it event A. This is proton abstraction. Proton abstraction, and the proton abstraction is followed by carbon-carbon double bond formation reaction, because the hydrogen cannot make two bonds or cannot be surrounded by more than 2 electrons. So the hydrogen-carbon bond is broken at the same time, and for a new carbon-carbon double bond is formed also at the same time, followed by departure of the leaving group. So this event, or event B, let's call it event B here, this is formation of a carbon-carbon double bond. So this is the second event in the elimination reaction. The last event, event C, is departure of the leaving group. So there are 3 events again: proton abstraction, formation of a carbon-carbon double bond, and departure of the leaving group. If the three events take place simultaneously, the elimination reaction is E2. So this is a one-step elimination, therefore. One step that consists of three events that take place at the same time. This is a one-step elimination. This is a one-step elimination where the three events take place at the same time. And this happens, then this alkene is produced. This is the alkene plus, as you can imagine, plus BH, the conjugate acid of the base, plus X minus. So this is the leaving group. So this is the alkene. This is the conjugate acid of the base that is used, and this is the halide, or you can also say this is the leaving group in general. So this is the reaction scheme of the E2 reaction or E2 mechanism. The E2 mechanism is a one-step elimination reaction where the three events of elimination, proton abstraction, formation of a carbon-carbon double bond, and departure of the leaving group take place at the same time. It is second-order kinetics, so the rate of the reaction will depend on the concentration of both molecules. It's bimolecular, remember, both molecules, which means the base and Rx, let's say, or the substrate in general. So therefore, it is second-order kinetics elimination. This is second-order kinetics, second-order kinetics elimination. It's bimolecular elimination. It is E2, and of course, if it's a one-step elimination, therefore there are no intermediates here. This is similar to SN2 reactions. E2 reactions are similar to SN2 reactions. That's because both are second-order kinetics types, and no intermediates involved in those reactions. Energy diagrams, their corresponding energy diagrams should be simple energy diagrams with no intermediates, only transition states, no minima in between reactants and product. There's no minimum, if you like, between reactants and products. It's a one-step reaction. The elimination E2 is a one-step elimination. SN2 is a one-step substitution. So their energy diagrams should be something like this, okay? So no intermediates at all. This energy diagram is a representation or energy diagram representation for E2 and also SN2, because both of them have no intermediates, only transition states, so that energy diagram is suitable to represent them. A summary of this video is that if the three events of elimination reactions, proton abstraction, formation of a carbon-carbon double bond, and departure of the leaving group, if the three events take place at the same time or simultaneously, then the mechanism type is E2. It's a second-order kinetic elimination or bimolecular elimination. There are no intermediates in this reaction. A very important feature of E2 reactions is the strength of the base. If you remember this E2 mechanism, the base should be able to take off a proton from a nearby carbon to the carbon that has the leaving group, proton abstraction, with simultaneous carbon-carbon double bond formation and departure of the leaving group. For this E2 reaction to be E2, or for the three events to take place simultaneously, the base should be strong. So the base should be strong for it to be able to do this three events in one go or in one step. This is similar to the strength of nucleophiles, if you remember, in SN2 reactions. The nucleophile in SN2 reactions should be small and strong for them to be able to attack the electrophilic carbon and with simultaneous departure of the leaving group. Okay, so the two reactions are similar in that sense. The base here should be strong. Examples of strong bases are alkoxides in general. So this is a general structure of an alkoxide. Examples of alkoxide would be sodium methoxide, or methoxide ion. It could be sodium, it could be potassium, so the methoxide ion, where R is CH3 or a methyl group. Ethoxide ion, and even the bulky T-butoxide ion. So T-butoxide ion, this is an example of a strong bulky base. These three are, and there are of course more, these are only selected three examples of alkoxides that could be used in E2 reactions. So an example of an E2 reaction, if you take this alkyl iodide, and then you treat it with sodium methoxide. So sodium methoxide will behave as a base, and that base will affect elimination reaction here. And the elimination reaction here will be loss of a proton from carbon 2. So this is carbon 1, this is carbon 1, that's carbon 2. So the hydrogen will be, or the proton will be lost from carbon 2, and the double bond will be between carbon 2 and carbon 1. So this is the product that is obtained in this case. This is the product, the alkene product that's obtained in this case, plus methanol plus sodium iodide as byproducts. So sodium methoxide is going to remove a hydrogen from here with simultaneous formation of carbon-carbon double bond here and departure of the iodide. So that's the alkene that's produced. This is an example of an E2 reaction. Another important feature or consideration, if you like, of E2 reactions is the conformation of the starting alkene, and especially starting alkyl halide, and especially if this alkyl halide is chiral. So if we take an alkyl halide like this, and here we say Br this time, CH2 here, CH3, and here CH3. So if we have this alkyl halide, and then we treat this alkyl halide with sodium ethoxide this time. So sodium ethoxide. So an elimination reaction is expected to take place. This Br is expected to leave from that carbon, and one hydrogen from a nearby carbon should be lost. A very important feature of the E2 reaction is the conformation of the starting alkyl halide, is that the hydrogen to be lost, and the two carbons where they would be doubly bonded in the alkene product, the vinyl alkene product, and the departing group should be on the same plane. So we can show this like this in general, so HL. So hydrogen, the participating carbons, that will be doubly bonded in the alkene product, and the leaving group, the 4 atoms should be on the same plane. So they should be on the same plane. The 4 atoms should be therefore planar. Okay, and that's why this is called periplanar. So this is periplanar geometry, but also hydrogen and L. If you view this general representation directly on through the carbon-carbon double bond, you will notice that the dihedral angle between H and L is 180 degrees. If you look through the carbon-carbon double bond here, or from there, you will see that hydrogen and L are 180 degrees apart, or the dihedral angle between H and L is 180 degrees, and therefore that could be described as anti. So that's why this kind of conformation or geometry is anti-periplanar geometry. Anti-periplanar geometry, this is our conformation, this is the most reactive conformation in E2 reactions. Yeah, so this is ideal for E2 reactions, ideal for E2 reactions. Yeah, and of course the base will come, take off that hydrogen, a double bond here will form, and will go. So in that case, a product of that alkyl halide would be this formation of a carbon-carbon double bond between these 2 carbons. That hydrogen is lost, that Br is lost, so we have a methyl group here. If you watch the stereochemistry, this methyl group on this carbon and that methyl group on that carbon are trans with each other. Yeah, so they will also be trans with each other. And the ethyl group on this carbon and hydrogen on that carbon are also trans with each other. So that will also be maintained. So CH2 here, CH3, okay, and hydrogen. The ethyl group and hydrogen, are trans, they are also trans here. The methyl group here and this methyl group here, they are trans, they are also trans here. So this is the alkene that is produced in this case, and if you want to determine a double bond geometry, you will notice that the methyl group is of a higher priority than hydrogen, so 1, 2, 1, 2 here, okay, and 1 here, and 2 for the methyl group. So the ethyl group is of a higher priority than the methyl group, and therefore the double bond geometry in this case is Z, because you have higher on one side of the carbon-carbon double bond, or lower. We can also draw a Newman projection, by the way, for the starting alkene, because here we are using terms that we used before when we talked about Newman projections. Yeah. So if we view this reactant or this alkyl halide directly on like that, that's your eye, remember? Yeah, so you look through the carbon-carbon double bond directly on. So what will we get? We will get a Newman projection of this type. So H will be up, H up, and if we look through the carbon-carbon double bond directly on like that, then this ethyl group will be on our right side, and the methyl group is on our left side. So ethyl group here, and methyl group here. What about the back carbon? Well, the back carbon will have Br, you see, if we look again through the CC bond, H up, Br down. So Br should be 180 degrees away from hydrogen, yeah, but it's on the back carbon, which we don't actually show. So Br here, and on the right side will be CH3. So CH3 and this ethyl group, by the way, they are both heavy wedged, yeah? So they should be together, if you like, or cis, if you like, yeah? So methyl group will be on our right side, on the back carbon, with respect to the back carbon, and H will be on the left. So methyl group here on our right, and hydrogen here on our left. And if you recall, the best way to draw Newman projections here is that this bond on the front carbon and that bond on the back carbon are opposite to each other directly. This bond on the front carbon and that bond on the back carbon are also opposite. That bond on the back carbon and this bond on the front carbon are also opposite. This is a staggered type drawing of a Newman projection, and you notice that hydrogen and Br, see these are again the contributing atoms, hydrogen, carbon, carbon, and Br, it's anti-paraplane, you see HCCl, yeah, HCCl, yeah? Okay, this is anti-paraplanar geometry. You will notice that H and Br, so H and L, H and Br are anti, so they are 180 degree apart from each other, and this fits this description, that this Newman projection is anti with respect to H and Br. H is the proton to be abstracted, and Br is the group to leave, and of course the two carbons are the front carbon, which is shown here, and the back carbon. So to conclude this lecture of E2 reactions is that the base in E2 reaction should be strong for it to do the three events in one step for the base to be able to abstract a proton with simultaneous carbon-carbon double bond formation and departure of the leaving group to take place at the same time. The base should be strong. The examples are alkoxides. A very important feature of the E2 reaction is the geometry of the starting alkyl halide. The best geometry or conformation of the starting alkyl halide should be anti-paraplanar as shown. And if that's the case, then an alkene is produced, and of course if alkenes are produced, then double bond geometries can be easily determined.